In this video, we're going to look at another example of how to compute an area under a graph or an area between graphs as a sum of slices. And the visualization here is consistent no matter what the example is. We're going to take some region, we're going to decide along which axis we're going to slice it, and that'll leave us with either rectangles like these ones here, where we consider the small unit of delta x as the width, or we would have rectangles like this bounded on our function, and in those cases delta y would be the width or the height, depending on how you want to phrase it, of these rectangles here. Once we've decided on our direction of slicing, we try to find the size of a generic slice, and that can be either the height of the shape, in this case here, height of the rectangles if we're slicing this way, or the width if we're slicing horizontally. We then write out a sum that represents the total as we add up all of the different rectangles, turn that into an integral, which is usually the easy part, and then evaluate the integral, which can be hard or easy depending on the formula we ended up with. Let's consider an example where we find the area enclosed between the graphs of x equals y squared, which is the sideways parabola, and the graph of x equals y, which is this straight line here. Let's label those first. And once we have the picture, we can see the enclosed region. So it's all this part trapped between the two lines. We're then asked to compute the area of that region using horizontal slices. So it never hurts to draw these just to make the example concrete. And what we see is, depending on where we draw our slice, we're going to get different widths. And width here means the horizontal distance. So our next step is to find a formula for the dimensions, and in particular for that width. So the area of a slice, and let's make this more specific, at location y. So imagine going up to some y value and finding the width. Well, that's going to be one of the ingredients, and the height is going to be the other ingredient for the area of the rectangle. And that's going to give us, the height is the easy part, it's delta y. And for the width, I like to do it again as a two-stage construction. This is a distance in x. I'm not going to call it a delta x because deltas are usually something very, very small when we're talking about integrals, but it is an x high minus an x low. I'll write that more of a subscript. So x high is here, and x low is down here. That might seem a little counterintuitive because this graph is on top, but look for the highest y value, and then, sorry, let's go back. That might seem a little counterintuitive because this graph looks like it's above the straight line y equals x, but if we look at just the x direction, this is a larger x value than this x value here. So if I want to find the width, I would take this x minus that x. So if that makes sense, then the next challenge is to bring it back to the formulas. X high is the x value on the line y equals x. Oh, well, if x is equal to y, and we want to find this at a location y, we're going to do that through a little conversion. Let's do this explicitly here. On the graph y equals x, the x high can be translated into just y. On the x low graph, that's the graph defined by x equals y squared, so I can take that x value and replace it with y squared. And we keep the delta y. So this y minus y squared gives us the location. You give me a y value, I'll tell you what the x value is, that's y. I'll subtract off the location of the parabola, that's y squared. That'll give us a width overall. Then we multiply by the little unit of height, delta y here, and that gives you the area of the slice. Going back a slide to the instructions or the guidelines, we've decided the axis, we found the area of a generic slice, which is perfect, and we just need to write out the sum and then the integral, and then we can evaluate. So you can even skip the sum step if you like, but the sum of the total area is going to be approximately adding all these things up. Y minus y squareds times delta y's, and we just slide those little subscripts in here to say we take different y's as we go up and through the scale here, or the total area is exactly equal to the integral of, going back to the generic slice, y minus y squared, and the delta y gets converted to a dy, indicating an infinitesimal or a limit as delta y goes to 0 of the heights. And then the last thing we need to include are the bounds of the integral. In this case here, the first slice corresponds to the y value of 0. We slice, 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 slice. The last slice corresponds to y equals 1, and that becomes our integral. The area enclosed between these two graphs is going to be defined by this. We'll do the calculation for this on the next page. So we found our area between the two graphs was defined by this integral. Now we can simply add 1 to the power, divide by the new power, do the same thing for the y squared turning into y cubed minus 3. All of those are going to be evaluated at 1 and then at 0. We plug in the 1, we get a half. We plug in the 1, we get a third. Minus, plugging in the 0 and the 0 gives us not a lot. And at the end of the day, a half minus a third is equal to 1/6. So this region here has area exactly equal to 1/6 of a square unit. Now, does that seem at all reasonable? Well, if we imagine this half unit here, now does that seem at all reasonable? Well, the entire unit here would be 1 square unit from 1 to 1, and we're certainly less than half of that. In fact, about a third of 1/2, about 1/6. Yeah, that seems eminently reasonable given what we see in the diagram here. The key thing for us now, though, is the construction of the area of these rectangles. How can I define the area between graphs? It's simply by looking at rectangles and being careful about how you define the width and the height of them. Once you have that height and width, building the integral is easy. We essentially wrap it around with an integral sign and convert the delta y or delta x to a dy or dx, and we're ready to go. The tough part is setting up the area of the slice as the building block towards that.